Yeah, so my name's Kyle Foreman. I'm the head of the data science group at the Institute for Health Metrics and Evaluation, which is at the University of Washington. And I'm going to talk a bit about how we're using Spark in our forecasting platform, which is we're supposed to come up with what's the likely future of the disease burden in the world based on what we've seen in the past and under all sorts of different possible scenarios. I'll give you a little bit of context about what we do at IHME, because we kind of run in very different circles than you guys, so just a little bit of context might be nice. So we're an independent research center at UW, and we are mostly funded by the Bill and Melinda Gates Foundation and the state of Washington. And our goal is to provide objective measurement and prediction of all sorts of different global health and some global development measures. We've got about 300 people now. We've grown from, started, I guess it was a little less than 10 years ago in Seattle. When I started there, it was 30 people. We're up to 300 now, and we're about to ramp up to 500 in the next couple of years. And so the big questions we're trying to answer are, what are the world's major health problems? It's actually, in many places, harder to estimate that than you might expect. There's not data there necessarily. We want to look at how well society is addressing these problems, and then how we should allocate resources in order to best improve the world's health. The main way we do this is through a big project called the Global Burden of Disease, where we're trying to quantify the comparative magnitude of health loss due to diseases, injuries, and risk factors. So what we do is we look at a comprehensive set of diseases and injuries that cover basically any way anyone could lose their life or be disabled. And we do this for every single country. We do it from 1990 through 2015, and then we also look at how you attribute those to different risk factors. So this on the right here is a tree map of what are the major causes of death in the world. Blue being non-communicable diseases. That's things like heart attacks or cancer or asthma, things like that. And then green is injuries, so that includes road traffic injuries, homicides, wars, suicide. And then on the red, that is communicable diseases, so that's diarrheal infections or pneumococcal infections in children, or HIV and tuberculosis, things like that. And we work with over 1,100 experts in over 100 different countries as part of this study. So every year it comes out in the Lancet Medical Journal and has a gigantic author list where we have data on all these things. And all that data is available for download from us. And if you're looking for interesting data sets, we've got a lot of them on the Global Health Data Exchange, which is ghdx.org. So to give you an idea of what sorts of results we look at, here's the age standardized death rate. So that just means based on a common age pattern applied to all countries, red being the worst and blue being the best. Where do countries rank in 2013? So you can see that there's actually not as much difference as you might expect between North America, Latin America, Europe, Australia, a lot of Asia Pacific, and then Sub-Saharan Africa in particular is pretty far below, as well as some parts of Asia. And then also we pay a lot of attention to the childhood death rate, so that's kids dying under 5. So again, all this data is available for you to play around with. And then we also look at something called DALYs, which is disability adjusted life years, and that just means how do we quantify on the same scale both deaths and things that don't kill you but make your life worse. So for instance, we can put on here MDD right here is major depressive disorders. So by quantifying how many people have depression and on a scale of 0 to 1, how big that impairment is, we can say, not just what kills you as important things to target in terms of global health, but also what causes disability. So this is in high income countries. You can see it's mostly blue, which again is the non-communicable diseases, whereas in the lower and middle income countries, the burden is still largely with the communicable diseases. Those are things that we mostly have cures for, but actually getting them out into practice is much harder. So that just gives you an idea of what we do at IHME. And now I'll talk about why we need Spark to help us do some of this research. So the next big project we're doing is taking the global burden of disease and doing forecasts of it. So what is the state of the world's health going to look like in 25 years? Kind of the big impetus for this is, one, so people can plan things like pensions and health insurance. You need to know what the structure of the population might look like in 25 years to do that. But also it's that places like the Gates Foundation and various NGOs realize that any of these interventions they have for global health take several years to have any effect, oftentimes decades. So if you're looking at the state of today's health, well, that doesn't necessarily reflect what you should invest in if you want to save lives in 25 years. So we create a baseline scenario and say, what's the most likely state of the burden of disease in the world in 25 years? And we take into account all the relationships between mortality and morbidity and population and all the risk factors. And we do this for everything in the GBD. And then we also want to create a comprehensive framework to assess various alternative scenarios. So we say, what's the most likely trend based on the past, but also what happens if we see accelerated global warming leading to both more food insecurity, so droughts causing poorer crops, which leads to more malnutrition, and at the same time it also maybe changes the environment in which mosquitoes thrive and can spread malaria. So that would be one. Another one could be, what would happen if we outlawed smoking globally, and what would we expect the life expectancy in 25 years to be based on that? And we want to be able to just incorporate all sorts of different questions like this so that policymakers can think about where should we invest resources to change people's behavior or implement new vaccines, any sort of intervention you can think of, what's the likely effect on global health? So an important part about this is most analyses that do this don't take into account all the complex interdependencies there. Like I mentioned, with global warming, the change in temperature can affect everything from mosquitoes to food supply to even just the outside temperature affects how often people have heart attacks. And if you look at just any one piece of this, you're not actually capturing everything that you need to get an accurate assessment of what might change in the future. So we build this large simulation to take into account all of these factors and all the relationships between them. And then we also use it to test our sensitivity to different assumptions. Like, well, what if we assume that GDP is going up by 2% every year, but it's actually 2.5%? We can incorporate all these different scenarios and get large uncertainty intervals and that better reflect the true uncertainty around what the future is actually going to look like. So the basic process we use for this is we fit some statistical models using a plug for something called PyMB, just a wrapper we have around something called TMB, Template Model Builder, which uses automatic differentiation to really quickly solve models with hundreds of thousands of parameters in them. And then that's not using Spark or anything. But then once we have all those parameters, we can draw from the uncertainty distributions of those that incorporate all the correlations between them and our uncertainty around them. And then we can finally run through Monte Carlo simulations to update each of the things we're measuring over time. So each cause of death, each risk factor, and do that for every country, every age, sex, et cetera. And so that's where Spark comes in. So first I'll tell you a little bit about this thing we've built called SimBuilder. The goal of SimBuilder is to make it so you can easily design, run, and analyze these sorts of simulations. The main thing it does is help you build DAGs. So it will construct a DAG and validate that it is in fact acyclic, et cetera, and that you don't have any issues with alignment or anything. And so you start out, and we've tried to do everything, as you can see here, with really standard tools and just built on top of those. So you take a YAML file and you describe each quantity in your simulation. So each disease, each risk factor, and then you can use SimPy to explain. So that's just symbolic math on how each thing gets updated over time. So you can say, and I'll give an example of this in a second, that my ischemic heart disease death rate in time t depends on my ischemic heart disease rate in time t minus 1, so the previous year's version, as well as any change in blood pressure that year. That's a very simplistic example, but it allows you to specify things like that. And then we also use curses to make an explorer where you can jump through different levels of the DAG and analyze all their properties. It has a graph viz, so it'll output a visualization so you can actually see what your DAG looks like. And then it also allows you to execute that DAG to compute what the values would be in the future. And we have a couple different backends, and that's what we'll be talking about in a little more depth. One that just uses pandas, and another that uses PySpark. So an example is, this is just like a very small part. We're doing a couple hundred diseases, both death and morbidity, and 70 risk factors. And each of these is by country, age, sex, etc. But journal will say we have GDP, and we want to predict next year's deaths. Well, a good indication is this year's deaths, and maybe the change in GDP also changes the mortality rate. And then we want to look at births, so we can use last year's births as well as last year's GDP, gives us a good idea of how many kids are going to be born. We can combine the deaths and the births with the previous year's population to get the new population. That changes what the structure of the population is and how many people are available to work, which itself then has a big effect on GDP. So again, this is a very small piece and kind of a stylized example, but that's the sort of thing we're trying to run. So for this one, we'll create a YAML file that describes the overall simulation, and then we'll specify what the different child models are. So in this case, a model would be GDP is one, GDP per capita, population, mortality. Each of those would be a model. And then we build a separate file for each of those. You say, what are the dimensions along it varies? Does it change by country, by year, by draw of the uncertainty interval? Does it differ by age or not? And then you give it an expression on how to update that quantity over time. And then you run SimBuilder to validate, and allows you to explore the DAG. So here's an example. This is the sim file, and this just describes what the total simulation looks like. So you just give it a name, and then you say, what are the models? These are basically like the different children within the DAG. And then you can say, what are the different things this varies over? So each location, there can be, we could say, we have 188 different locations in our case. We can also say time. We say that goes from 2014 to 2040, and then how many draws from the uncertainty interval are we running through? And then for each model, so one would be population. Population, we already have forecasts of that through the UN, for instance. So we just say, it differs by location and year, but we don't have draws from the uncertainty interval of that. So it only differs by location and time. And then we just tell it, oh, there's a CSV file located here, and it knows how to load that in and run for the simulation. Something more complicated like GDP per capita, we give it an expression here that says the GDP for a particular draw, year, location, per capita equals the GDP divided by the population from the previous year to make it acyclic in this case. And then we give it, we say this varies over these three variables. And again, we tell it where to find the data. And then you can get really complicated. This would be how we actually calculate GDP itself. And this is an example of alpha and beta, all those are themselves outputs from the statistical model that we've fit. And so we can just save those parameters and use those when we're running the actual simulation. And then each of those can themselves be a separate CSV file or HDF file. There's a lot of different options on how to do that. And then once you run that, first you can just output a quick visualization of the DAG. So this is just given those YAML files I showed you a second ago. This is what the DAG for a single year looks like. And so you can see it has all of our parameters leading into each step along the way. And then you can additionally say, what does it look like for a longer time period? So this is if we look at 2 years, the little curly bracket subscripts at the end, that's a year, so year 0 and then year 1. And I'm not going to show the whole 25, but even if just 5 years, you can see the DAG gets really complex. And in our case, this is about 1/1000th of the total nodes that we actually use. So once you've built that DAG and need to execute it, we have a couple different options on how you do that. And this is something we're still testing out, but we found some interesting findings in terms of what works best for these sorts of simulations. So this sim builder itself traverses the DAG, and then the backends just plug into it via an API. They just need to provide some way of loading data, combining data from different nodes to produce, the new value in T+1, and then some method to save what's been computed. So the first one we did was just using pandas. So this was really useful for running really small things like that example I just showed you. And basically, it's just we have some master process. We have a list of models. So we have one for GDP, one for GDP per capita, one for population, mortality. And each of those is just a pandas data frame. And then we index it based on those global variables, like location, age, sex, draw. And then you give a little SymPy expression to say how to calculate the value in T+1. And it just executes them sequentially and will join the DAGs as necessary, and then basically add in a new column with the value in T+1 and then T+2 as it goes through. So that was the first one we built. And it's very simple, works well, but of course it's not going to scale very well once you get beyond whatever you can hold in memory. So our next thing that we tried was just to move to using Spark data frames directly as the backend. And the idea behind that is, well, it's very simple to just kind of replace the pandas data frame with that. Lots of little tweaks we had to do along the way to enable that. And there are a couple limitations, such as we can't use the vectorized operations on two columns like you can on a pandas data frame. It's really effectively doing it as a row-wise apply. But otherwise, it works pretty well. And the main limitation is that it ends up doing a lot of joins between them, which I'll talk about in a second. And so the latest one we've been using is actually just using Spark to distribute Numpy arrays around. And the idea is that we have a very consistent shape for our data. We know it's always going to be countries by ages, by sexes, by locations, by years, by draws. So we can have this 5 or 6 dimensional array, and we know it's always going to be filled and in that exact same order. So why do we need to make our data long in a data frame and then try to join on those keys when instead we just have this 5 or 6 dimensional array? And so what we did is then we just put each of those arrays, one for each quantity, like here's our GDP array, here's our population array, and we put each of those in an RDD. To start with, it was just one RDD and one NumPy array. Then we've started doing some things like splitting up along one axis into different partitions within an RDD, which is really similar to what Bolt does, I believe. And then when you need to compute a new node, you just join the parent RDDs together and do vectorized operations on those NumPy arrays. And what we found is when we test these 3 things, this is all just using a single executor. This is not using our full Spark cluster, but just to kind of get a test of it. And we've built some synthetic data that we can use here. It's not very big, but it's big enough that it kind of almost fills in the pandas local runner when we get up to 10,000 draws or so. And the time to run this forecast, you can see the dark blue line there is using pandas, and then the second line there is using the Spark data frame, and the bottom one is using NumPy arrays instead. And we found that the pandas one quickly falls off the wagon, and we can't use it. We weren't even able to run it for all 10,000 draws more than once or twice. But then the others, they scale really well, and we find once you get above, really even at just 100 draws, we find that the NumPy version is much faster. And so this again is how many for one of our dimensions in the array, that's how many draws from the uncertainty distribution we've done. This is just varying the number of those. And eventually we want to get up to like the 100,000 draw range, and then all the other dimensions will be much larger and a lot more nodes. So this is a very small version of what we actually need to run in the long term. And we also find that if we give more cores to the Numpy executors, well, you can take advantage of the multi-threading of the Numpy library, and we can get it quite a bit faster even by increasing that. It's not quite linear scaling with the number of cores, but it's not too far from it. So what we found is that using the Spark DataFrame was sort of limiting in terms of the actual execution speed. It made things really easy for us to translate our pandas code that we'd already written and ran locally into something that we could distribute. But we lost the ability to take advantage of a lot of these vectorized operations that NumPy and a lot of the underlying libraries that it uses have been optimizing for years. So if you need to add two big matrices together, well, adding those together versus doing, joining two different data frames together and then going row by row and adding them, it's just a lot more efficient to use the vectorized operations. And in our case, execution time is going to be an important factor for it. So we wanted to make sure that was ideal. We spent a long time working on tuning the various partitioning parameters and things like that for the Spark DataFrame version. I'm sure we could tweak it and get it better than we did. Not sure if we could come up with something that was faster than our NumPy version, especially once we get into much larger sizes, though. And so, yeah, the idea is that with these multi-dimensional data sets with a very consistent shape and size, all we have to do is align things. We're using Spark to pass them around, but we don't have to do the complex joins that were really killing our performance. And we've come up with something called a balanced in-dimensional panel that honestly we might just end up switching over to something like X-array or X-ray, whichever it's called now. But it's very similar to that, and it's just a way of coming up with a labeled array that you can easily combine and align the axes automatically. And we found that they also scale really well with the number of cores, just relying on simple MKL. For future development, we're thinking of maybe we can partition these NumPy RDDs into something in a more efficient way. Right now, we've just tried giving it a certain axis and splitting along that. Something like Bolt would be really attractive here. We hadn't used a Bolt in the past because it didn't have element-wise operations until about 2 weeks ago we saw it got committed. So it seems like a lot of what we need in order to run our simulations is falling into place there now. So I think we're going to try that as a backend as well instead of our little hacky custom version. And the other thing we need to work on is partial graph execution. So we find that once we get to really, really big DAGs where we have tens or hundreds of thousands of nodes in them, trying to call a collect on the last element there, then our master often ends up crashing. The driver crashes, just trying to compute what an optimal execution path there is. So what we do right now is we go through sequentially year by year and execute that graph and then go the next year and execute that. It means that we don't have to compute the whole thing at once, and we don't run on memory and crash the driver, but it also means that within the execution of each DAG, we are a bit slower than we could be, because there's some points when it gets towards the end of the DAG, and like the next DAG could be starting to execute, but it waits for the whole thing to finish, and maybe it's only using a small portion of the cores. So that's something we're trying to figure out, and would love any feedback on ideas for that. And then we're also going to keep tweaking the Spark DataFrame joining to see if we can get any improvements in that. For instance, the talk this morning about time series RDD that gave us some ideas on how we might actually be able to join those a little more efficiently. So all this work I presented, that just small part of the team. So we've also got Kyle and June here. So we'd love to hear any feedback on how we could improve our performance here. And we plan on, everything is up on Git, but it's not made public yet. And we're hoping to do that really soon. We're just finishing writing some tests for everything. But we'd love if anyone would like to collaborate on this or have ideas on how we can improve it. It'd be great. Thanks.
Great. We have time for questions. All the way in the back, of course. All right, meet in the middle.
Hey, what's up?
Hi.
Thanks for your talk. I have a functional question, not a geek question, even though I'm a geek. So I follow the Gates notes. He seems to be a big fan of measuring stuff. How is your organization measured on your success? Do you have like a methodology for measuring your predictions, and how do you guys track yourselves?
Yeah, so we have several different external advisory groups. We have 3 of them now, I believe, where we have, it's mostly professors, but also it's members of certain public health organizations and ministries of health that do biannual reviews of all our work. And in terms of, do we have a quantitative way of assessing that? It's hard to say. We do a lot of out-of-sample predictive validity and things like that to show that our models perform better than estimates put out by other groups. But yeah, how to evaluate the evaluations is a tricky question. I don't think anyone has a great answer for yet.
Next question here.
How do you anticipate medical advancements, since those can be somewhat random in terms of breakthroughs and things like that?
Mm-hmm. Yeah, so we do baseline forecasts, which is just kind of like business as usual. Based on the past rate of progress in treating a particular disease, what is the likely future rate of progress on that? So that will be what's in our baseline. And the reason we do 100,000 draws from this uncertainty distribution is there's also going to be a lot of noise in that sometimes there'll be big shifts from one year to the next where suddenly, the case fatality rate is halved or something. So hopefully the uncertainty will capture a lot of that, but then that's why we want to have, be able to do all these alternative scenario simulations where we can say, what happens if there is a new vaccine introduced that drops the incidence of this disease by 99%. And so that's where those alternatives come in. And we mostly work with people who are developing those vaccines and things like that to come up with a way to quantify that effect.
More questions?
Do you guys have a process or a workflow to introduce additional parameters into the model? For example, political forces, new discovered disease or whatnot, or even to increase the granularity of your political model? Say like, there's newly discovered genetic disorder, and all of a sudden you want to partition the population by, with or without that particular gene.
Yeah, so for instance, we had this recently with the global burden of disease with Ebola, where we needed to add in estimates of Ebola deaths. And so, like I said, we have 1,100 collaborators on this study. And so, we have working groups within that for specific diseases. So we have ones on, particular sets of communicable diseases or non-communicable diseases. And what we'll basically do is, convene a small group of them to get feedback on how we should incorporate this new disease or this new intervention. And then they'll make suggestions on how to model that. And then, we have the full pipeline, not totally automated yet, but we're working on getting that more and more automated so that we can eventually, plug in, like in this case, it would just be adding a new YAML file for that new disease, and then including that in the DAG, and we should be able to run it.
A quick follow-up question. So in case you're introducing a new parameter, how do you figure out the interdependency between that one and existing ones so that you're basically having a probabilistic graph model? You want to figure out a latent variable guiding the particular interdependency.
Yeah, so for a lot of that we use, for instance, risk factors is one of the big ones where we say that change in diet leads to change in blood pressure, leads to change in heart attacks. And how do we decide that those are the relationships there? Well, we use a lot of epidemiological literature reviews to find, where's there strong evidence of a relative risk of, systolic blood pressure affecting heart attacks or stroke or whatnot. And so we have a pretty stringent, we again use these expert groups to decide on is there enough evidence to say this is a risk factor for that. We're not just looking for simple correlations. We're not trying to just data mine this. We are attempting to incorporate a lot of the medical and epidemiological knowledge into how we build our models.
All right, thanks so much.
Thanks.
Man.